x which is not equal to 2. So I guess that's pretty much all you needed to write, or in other words, that vertical asymptote is actually at x is 2. So we're going to think of the graphing our function here that deals with this vertical asymptote with equation x equals to 2, just like that. So we need to actually graph in this section. So let me finish up with graphing, but all you have to do is just to say it's x is not equal to 2 or equal to 2, because if that point is out of domain, then pretty much automatically we get that vertical asymptote. So it looks like I need to also get a horizontal asymptote. And for that matter, we're going to have to get the quotient of the so-called leading coefficients. So the y, or f of x, is going to be equal to 1 divided by 1, which is equal to 1. So y is 1 is equation of my horizontal asymptote. So once I have a pair of the asymptotes, then I can produce a graph of this function. I just need to have some points, and I could utilize, instead of y, value of 0. Remember that y-axis intercept we produce when, x-axis intercept, we always try to get intersections with x-axis when y is equal to 0. We can also get an intersection with y-axis as well, but we always start with setting y equal to 0, and that ends up being 0 for our numerator. So when numerator is 0 and numerator is up here, then I can see that x is equal to -4. And this way, when I put a -4 someplace here on the x-axis, then I'll get a graph that passes through it and goes along my horizontal asymptote, and then it goes down along the, so along vertical and then down along the horizontal, so like that. And then the other piece will be in that upper corner in here, and the point is that it cannot intersect my x-axis again, because we just found only one point of intersection with that x-axis. That's why the graph must be above the axis, so there'll be no intersection. So again, this is the story of graphing and using the so-called asymptotes that we actually do in the sections related to college algebra. That's actually college algebra material. So today I would like to go back to the calculus story and to get the actual derivatives in use. And we already did this number of times, right? We saw that if we have the maximum, then tangent line at the maximum is horizontal, and derivative, the slope of it is 0. Or if we have a minimum, the tangent line is again horizontal, so derivative or slope of it is again equal to 0. And if we have this minimum point, turns out derivative is, if you look at the tangent line, is going to be vertical, so there is no slope, or derivative is not even defined. Well, that's the case we're not gonna really see, but those with the tangent lines being horizontal, so zero of derivatives, that's something that we already used number of times when we graphed. So there'll be nothing really different here. And that's why I'm gonna try an exercise here. So how about problem number 18 with the function f of x? Let me copy this here. The function will be f of x, which is the same as a 1 plus 6 times x and minus 3x to the second. So what I'm going to do is to take a derivative of that function, just like we already did before. And this will give us 6, and then 3 times 2, which is 6x. So once you found that derivative, then you're gonna set it equal to 0 right away. And this will be just what we need for graphing that looks like parabola, right? Parabola that will open down. So let me solve this for x. So I'm getting that x is equal to number 1. And this means that we have the special point 1 that I need to actually plot by finding its y coordinate. So we always plug this in the original function because that's what we're always trying to graph, right? So you get 1 plus 6x and then minus 3x to the second power. And then we're going to replace our letter x with number 1. So I'm going to go ahead and put number 1 here instead of x, and here instead of x as well. So we're going to get the number 10, right? This is equal to 10, and point with coordinates x is equal to 1 and y is equal to 10 will be someplace up here, 1 and then 10. And this is my vertex. Vertex for the parabola that will open down, so it'll go somehow with that, right? Parabola opens down. So now the question is, what should we do in order to get this 0, 4? So what are they talking about? Well, it turns out that they don't want to consider entire function. They want to consider just a little piece of this function that is in between 0 and 4, so probably ends someplace in here. So they don't look at the entire parabola. So they restrict the graph only on that particular little interval. And on that particular little interval, we're gonna have to calculate 2 more values of function. Value of function at x equal to 0 and the other value of function at x equal to 4. So let us do this. F of 0, again, I'm plugging the numbers into my original function, so it'll be 1 plus 6 times 0 minus 3 times 0 to the second, so this is equal to 1. And then f of number 4, which is analogously calculated, 1 plus 6, now we put 4, right? Minus 3 times 4 to the second. So let's see what we are going to get this way. Here I have 24, right? and then 3 multiplied by 16, which is equal to 48. Right? So when I subtract, get negative 24, and then 1, looks like it's a minus 23. So what we can do is notice that the largest value or maximum will be here at point 1, and that's what we can see on the picture, the largest value of function, or so-called maximum point, the vertex, and the lowest value of function is actually present at point 4. It is minus 23, so that's so-called minimum point. So there is a maximum, which is the largest, and there is a minimum, which is the smallest value of function. And this maximum and minimum is what I'm going to have to utilize for the answer of this exercise, simply because they want to know the largest and smallest values on that particular closed interval. So looks like we are not going anywhere, but we're just going to deal with the values for the function at the endpoints extra compared to what we did already before. So these things are added in this little section. And other than that, it's nothing else but the story about those derivatives. So I would say the rest of everything I could just disregard, because there'll be more sections with exact same ideas. So you get the graph, and all you have to do is take derivative, find it equal to 0, and that will be your maximum. So I guess I'm not gonna get much into this, because that deals with some geometric structures, and I know that most people probably not gonna be very happy with those, and that's why I'm gonna move to the next chapter, because now we're going to do some more work with derivatives. So chapter 3 is what I'm going to get to, and I'm starting section 1 of chapter 3. So it turns out we're gonna skip this rest, because it's all the same thing. It's all just take derivative and set it equal to 0. In fact, in the next sections, we're also going to take derivatives and set them equal to 0. So it's all pretty much the same story. But now it's for the special group of functions called power functions or exponential functions. And those functions are dealing with the number e, which is 2.178 ... Oh, sorry, 2.718. I just switched the digits. That's called dyslexia. 2.718, and etc. Turns out there is a special number e. It's a friend of number pi, that here is 3.14, that we're gonna deal with in section 3.1, and that number e is what we're gonna be actually working with from now and on. So they're talking about the graphs of various exponential or power functions. So for example, here they considering 2 to the power of x. And the graph of that function is something that passes through point 1 on the x-axis and keeps going up. So we put the arrow to show it. So the horizontal asymptote is what we're utilizing in here. So why is it passing through point 1? Well, actually, it's a point 1 on the y-axis, so it's a pair with coordinates 0 and 1. So actually, x is equal to 0 and y is equal to 1. So instead of y, if I put 1, and instead of x, if I put 0, notice that indeed 0 power is always equal to 1. And that's why the graph looks like that, passes through point 1 as they made on the picture. And they also check this out. They plot a bunch of points here and they connected them with this exponential function. So it's good to be aware that those power functions, they always pass through point 1. And actually, if they're looking at general function with the exponents, so right now I'm gonna take a look at the graph of function, say any letter a to the power of x, then they all gonna be passing through point 1 on the y-axis. So that's a common thing about all of these functions. So looks like if I try to graph y is equal to e to the power of x, it's also going to be in the same shape. So it's also going to be passing through point 1 on the y-axis. And it has same horizontal asymptote, which is my x-axis. So we're going to deal with this e to the power. And again, that number e is just a number a little bit more than 2. It's 2.7. It turns out it's a very convenient number to work with. And that's why we're actually dealing with that graph of e raised to the power of x. So I'm going to be bringing us here to the exercises that actually want to take some of the derivatives. So here is one more formula that we need to utilize in this chapter that says that derivative of e to the power of x is exactly the same e to the power of x. I think that's probably the nicest formula that I ever encountered. And we're gonna use this new formula and doing the exercises in section 3.1. So I'm gonna look at the function f of x equals to e to the power of negative x. So how about finding its derivative? Well, looks like derivative of e to the power is the same thing, e to whatever power it is. But then I need to multiply it by the derivative of your exponent. And remember that derivative of x was 1. So what about derivative of minus x? Well, this is negative 1. So my derivative is actually negative e to the power of minus x, just like that. So I found derivative of the function. Let's try to do this again. How about exercise number 17? Let's try to find one more derivative here. In exercise number 17, I have e to the power of negative 7x. So I'm gonna try to take its derivative. And again, e to whatever power, I just copy the way it is because that's my formula that says take derivative, you get the same thing. But then I need to multiply this by the derivative of my negative 7x, right? The chain rule. And this is just a -7. So the answer is going to be -7 e to the power of -7x, just like that. So it looks like we're getting this formula in use along with a favorite chain rule. So let us practice. Let us use this formula again. How about if I try exercise 45? That says you have the a square root function extracted from e to the x minus 1. So take derivative of that. Well, when I differentiate the square root, this is going to be 1 over 2 square roots, right, of this e to the x minus 1. And then I'm going to multiply this by the derivative of what's inside the square root. And this will be e to the power of x, because again, that's our new formula. When I say, what about -1? Well, derivative of -1 is just the same 0 because it's a constant, so we totally disregard that. Okay, so let's do one more here, and then maybe you can try one, right? So it looks like that's probably the nicest formula for derivatives that we encounter. So how about exercise number 21? And then you can try to do 22. So I'll do number 21 here. That says -3 times e to the power of -x that I will be differentiating. So it looks like -3 is going to stay because that's a constant that we multiply by something. So it stays unchanged. Then I'm going to take derivative of e to the power of -x, and that'd be exact same thing, e to the power of -x. And then I need to multiply this by the derivative of -x, which is -1. So I can simplify this a little bit and say 3 is multiplied by e to the power of -x is my result. Just like that. So it looks like here we have the result, and that's great. So we can have you try one, right? The exercise, was it 22? How about if you try this derivative as a little quiz for today? Exercise number 22. So you can, as usual, put in the Zoom chat the answer for this derivative of capital G of x. So that's a little quiz that you should try to take.